car has mass 1,200 kilograms. Its engine applies a driving force of 2,500 newtons. There is a resistance to motion of magnitude 400 newtons. The car starts from rest. Find the acceleration of the car. Now, I'm assuming that the car is moving to the right, and I'm going to take all vectors pointing to the right as positive vectors. So let's look at the forces acting on the car. Well, we have the driving force acting on the car. That force is produced by the engine, and the driving force is pointing in the direction of motion of the car, which is to the right. So I'll call this vector D. So D is going to be plus 2,500. I'll put in the plus sign to emphasize the direction. There are only two directions in this problem, positive and negative. Now we have a resistance to motion of magnitude 400 newtons. So this force points in a direction opposite to the motion of the car. So the resistance force points to the left, not surprisingly. I'm going to call this force R. Now, following our convention, vectors pointing to the right are positive, so vectors pointing to the left are negative. So vector R is minus 400 newtons. Now, what other forces act on the car? Well, we have the weight of the car acting vertically down, which we saw in the previous video is the mass of the car times the acceleration due to gravity, g. G is 9.81. However, this force here is balanced by an equal and opposite upward force. So this upward force has the same magnitude of this downward force. The upward force is present because the car is in contact with the ground and it's not falling through the ground. So the car is not accelerating up or down. So the net or resultant vertical force on the car must be zero. So we're really adding four forces here, but the two vertical forces cancel out to give zero. So we can ignore them in this problem. So ultimately we just have two forces acting on the car. To get the acceleration we need the resultant force on the car, so we need to get the sum of these two forces. Now in the previous video I used F for the resultant force. So we get the vector sum of all the forces acting on the object. So we need to sum these two vectors, R and D. It's easy to get the vector sum of these two forces because they're both lying on the same line. So we don't have to use any parallelogram law or triangle law. The resultant force is 2,100 newtons. It comes out to be positive, so the resultant force is pointing to the right in the positive direction. Now, Newton's second law tells us that the resultant force on any object is the mass of the object times the acceleration vector. So we need the acceleration. So the acceleration is the resultant force divided by the mass. So the resultant force is plus 2,100. And the mass of this car is 1,200 kilograms. So force is in newtons, mass is in kilograms. That means that acceleration will come out in the correct SI unit of meters per second squared. We see here that the acceleration comes out to be positive. Mass is always positive. So the acceleration is in the same direction as the resultant force. The resultant force is in the positive direction, so the acceleration will be in the positive direction. So the acceleration is also to the right. Here the white vector is the resultant force F, and the acceleration, which is just a scalar multiple of F, or you could say F is a scalar multiple of A. F is just the mass times A. A is in yellow. Its magnitude is 1.75. Next thing we want to do is find out how far the car will travel in the first 15 seconds. Now, the rest of this problem is just a problem in linear motion with constant acceleration. So, as long as these two forces are acting and they're constant, they don't change, then the resultant force is constant. That means it doesn't change. As long as it is acting, the acceleration is a constant, or uniform, 1.75 meters per second squared. So we're dealing with uniform motion, or linear motion with uniform acceleration. The initial velocity of the car, we are told, is 0 because the car starts from rest. And the car will be traveling for 15 seconds. So say this is the position of the car, 0 meters, and this is at time t equals 0. So we're interested in how far it will travel. S is used for distance. So we want to link up these quantities. Well, we know that for linear motion with constant acceleration, S equals ut plus a half at squared. So we just plug everything into this. So we have 0 times 15 plus a half times a, which is plus 1.75 times 15 squared. We get 196.875 meters. An object of mass 11 kilograms falls from rest through the air. Air resistance is a constant 18 newtons. Find the acceleration. So we have some object of mass 11 kilograms and it's falling through the air. It's falling from rest, so its initial velocity is 0. Let's look at the forces acting on it. So at the instant it falls, its velocity u is 0. I'm going to take the downwards direction as being positive, although it doesn't matter. You could work with upwards as positive also. So let's look at the forces acting on this object. Well, we know from a previous video that for any object near the Earth's surface, we have the force of gravity, or the weight, given by m times g, where g is the acceleration due to gravity. I've explained all this before. G is 9.81 for any mass near the Earth's surface. So we have to multiply 11 kilograms, which is the mass, by the acceleration due to gravity, which is 9.81. We get 107.91 newtons. Now I'm going to stress that we're dealing with vector quantities here. W is pointing in the downwards direction, so the sign of this vector gives us the direction. So this is plus. I put in the plus sign to emphasize the direction, and we have both direction and magnitude here. Now we have an air resistance force of 18 newtons. Now, resistance force acts in a direction opposite to the direction of motion of this object. So the resistance force must be pointing upwards, and its magnitude is a lot less than the magnitude of W actually. Its magnitude is 18 newtons. I'm going to call this force R. And because it's acting in the upwards direction, its sign is negative. So, to get the acceleration, we first need to get the resultant force on the object. Now, these are the only two forces acting on the object, and they're both constant forces. So, as the object is falling, provided it's near the surface of the Earth, then the weight is constant. And we're given that the air resistance is constant 18 newtons. So, no matter where the object is, you know, R and W remain constant. So, R is like this, just like it is here. It doesn't change. So, as the object is falling, these two forces acting on it don't change magnitude or direction. As usual, I'm calling the resultant force F. So it's very easy to add these two vectors because they're along the same line. And when we add them, we get plus 89.91. So the resultant vector is positive, which means that the resultant vector is pointing downwards. So I'll try and draw it in here. I'm going to draw it parallel to W because I can't show it directly on top of W. Its magnitude is going to be less than the magnitude of W because we've subtracted R. So here's vector F. It's acting in the positive or downwards direction. Next we apply Newton's second law, which says the resultant force on any object is the mass times the acceleration. So we turn that around, as you've seen already, to get the acceleration. So the force is positive. Mass is always positive. Now this object has a mass of 11 kilograms. So force in newtons, mass in kilograms, so the acceleration will be in meters per second squared. To 2 decimal places we get 8.17 meters per second squared. The acceleration comes out to be positive, of course, because the force is positive. Acceleration is always in the same direction as the resultant force, of course. So the object is accelerating downwards. So its speed is increasing in the downwards direction by 8.17 meters per second each second. Now we want to find the distance covered in the first 10 seconds. So initially the object is here. U is 0. Its initial velocity is 0. So we're interested in the distance after 10 seconds. So when U is 0, T is 0. So the timer starts when the object is dropped from rest. So we want S, which stands for the distance travelled. So we use this formula here to connect up A, U and T. Now this is actually a vector equation when we're dealing with vectors in one dimension. So, you know, the sign of S makes sense. We get plus 408.5 because the object moves from this initial position to some later position here. So the S vector, or the position vector, is pointing in the positive direction. So vector S is plus 408.5 meters. Now I'm going to call the distance travelled in the first 10 seconds S1. So the object here is at this position at t equals 10. We are interested in getting the distance covered in the next 10 seconds. So to do that, we can get the distance covered in 20 seconds. So we can replace t here with 20 seconds in this formula. Calculating this, we get 1,634 meters. So that gives us S2. So now we are interested in the distance travelled by the object from t equals 10 to t equals 20 seconds. So we just want this distance here. So it's just a matter of subtracting these two numbers. So I'm calling this distance d. It is 1,225.5 meters. A bullet is fired horizontally at 300 meters per second. It enters a fixed piece of wood which is 10 centimeters long and emerges at 200 meters per second. If the resistance of the wood is a constant 2,500 newtons, 25,000 newtons, find the mass of the bullet. So here's a piece of wood that is fixed to some bench or whatever, and it's 10 centimeters long, which is 0.1 meters. Here is a picture of the bullet just before it enters the block. Let's look at the forces acting on the bullet just as it enters the block. We are given that the resistance of the wood is a constant 25,000 newtons. So we have a force on the bullet which is opposite in direction to the velocity of the bullet. So the bullet is moving to the right. So we're taking vectors to the right as being positive vectors, say. So we have a force on the bullet which is opposite this positive direction, so it's in the negative direction. So I'll call this resistance force R. R is going to be minus 25,000 newtons. Now, this force is constant, so even when the bullet is, as the bullet is passing through the block, the same resistance force is acting on the bullet. So it's going to be the same, that is pointing to the left with magnitude 25,000. So that same force is acting on the bullet all the way as it passes through the block. Now we want the resultant force on the bullet. You might say that gravity is acting on the bullet, and indeed it is. Gravity is vertically down. Force of gravity is just the weight of the bullet, mg. We ignore the weight of the bullet since it is perpendicular to the initial velocity u equals plus 300 meters per second. The weight force, or the force of gravity, mg, has no component in the direction of the horizontal component of the velocity, and therefore does not affect the horizontal component of the velocity. So really, when we're applying Newton's second law here, we're just applying it to the x component of the resultant force on the bullet. The y component would be the weight of the bullet. Again, I'm using the letter F for the resultant force on the bullet, just to emphasize that we're talking about the horizontal component of the resultant force. I will write a subscript x, so x means the horizontal direction. So we can apply Newton's second law in just any particular direction we like. So that means we look at the weight of the bullet and we look at its x component. Well, its x component is 0, so it doesn't appear here. Newton's second law then tells us that the x component of the resultant force is the mass of the bullet times the x component of the resultant acceleration. And to get the x component of the resultant acceleration, we just get it from the velocity vectors. So these velocity vectors are both horizontal vectors. Okay, we could say that they're the horizontal components, or the x components of the velocities. Well, we were given that the bullet was initially fired horizontally, so the initial velocity is all in the horizontal or x direction. Maybe the bullet fell through a slightly curved path as it emerged from the block, and its velocity when it emerged was not exactly horizontal, but you would expect it to be very nearly horizontal. Anyway, we take this velocity v to be the final velocity of the bullet. We're assuming it's entirely horizontal. And if v is not entirely horizontal, well, it's very nearly so, and its x component is plus 200. So this constant force acted on the bullet as it moved through the block. As I've already explained, when the bullet is anywhere within the block, the resultant horizontal force on it is to the left and has magnitude 25,000 newtons. Even just before it emerges from the block, the resultant horizontal force is minus 25,000. So to find the mass of the bullet, we just need to get the acceleration. And we can calculate the acceleration from this formula. This formula applies for constant acceleration. Well, there's a constant force on the bullet, so if there's a constant force on the bullet as it passes through the block, that means the acceleration of the bullet is constant. And we're dealing with linear motion. Well, at least if we look at the horizontal components of the velocities, we are dealing with linear motion. And basically, the velocities are essentially horizontal. So we rearrange this to get A, and we plug in for VU and S. S is the distance travelled. So the bullet enters here. This is 0 if you like, and it travels a distance of 0.1 meters. So V is 200, U is 300, and we divide by 2 times 0.1. We get the answer minus 250,000 meters per second squared. Now, the acceleration has come out to be negative. Well, we'd expect that, because the resultant force in the x direction is negative. So the acceleration has to be negative as well. It's in the same direction as the resultant force by Newton's second law. Now, knowing the acceleration, we can calculate the mass. Just plug this number in for A and divide across to get m. So if we do that, force is in newtons, acceleration is in meters per second squared, which means by Newton's second law the mass will come out to be in kilograms. So we get 0.1 kilograms. In the next question, we want to find the shortest piece of the same wood which could have brought the bullet to rest. So if the bullet is brought to rest, we want V to be 0 when the bullet emerges. So we just go back and use this formula again. A is minus 250,000. The acceleration of the bullet is pointing to the left because the bullet is decelerating, slowing down as it passes through the block. The acceleration is in the same direction as the resultant force. The initial velocity is positive. We want the final velocity to be 0. What we're interested in finding is s. So this is the unknown, the length of the block of wood. So we just rearrange this formula to find s. So s is v squared minus u squared divided by 2 times a. So we have 0 squared minus 300 squared divided by 2 times a, which is minus 250,000. Notice that s is going to come out to be positive. We get plus 0.18 meters, which is 18 centimeters. Just a brief note on why s is positive. Well, directions to the right, as we know, are positive. That's the convention that we started with. So when the bullet enters here, s is equal to 0. And thinking of s as a vector, s would be this vector here. It's pointing in the positive direction, and its magnitude is plus 0.18 meters, or 18 centimeters.